Okay, this is not an official list, but these are proofs that you need to learn that I've taken off someone off Twitter, I think last year. So I'm going to go through these as best I can, and we will go from there. The only one I'm not great at is this one here, because I've never seen it come up in any past paper questions, and I'm not really sure how to do the proof. I probably will be skipping that, but let's have a go. Okay, so series. We want to prove arithmetic sequence. So arithmetic, and we also got to prove geometric. Okay. So the sum of the first n terms of arithmetic sequence, you got the first term, and then we're gonna have the second term, a plus d, and then we're gonna have the third term, like so, and we're gonna go all the way until n minus 1 d. Okay. So what we're going to do here is I'm going to rewrite this here, but I'm going to write it backwards, if you will. So we're going to have the last term, which is n minus 1 d. The second last term, which would be n minus 2 d. All the way until our third term, which is a plus 2d. Our second term, and our first term. Okay. So what we're going to do, we're going to add them together. So two lots of the sum to the n terms. Okay. A plus the following. So we're going to get 2a plus n minus 1d. Okay. The second last term and the second term, you're going to get again 2a plus, we've got n minus 2d plus d. So, well, these are like terms. So n minus 2 plus 1 is n minus 1. Okay. What do we notice? Do we notice how they're the same? And that's going to happen on every pair. Okay, interesting. Well, how many pairs of numbers do we have? We have n numbers. So this means two lots of the sum to the n terms is n lots of 2a plus n minus 1. So the sum of the first n terms is, we halved it, is n over 2, 2a plus n minus 1d. And there you are, that's your proof. That is your formula. Done. Okay, geometric. Let's have a look at it. So let's write the sum of the n terms, the first term, plus the second term, a times the common ratio r, plus this, the third term, r squared, and we're going to go all the way to the last term. Well, the second last term would be n minus 2, and the last term would be n minus 1. Fantastic. Okay, this one's a little bit different. I'm going to multiply this by the common ratio r. So sum to n. So you're going to get AR plus AR squared plus AR cubed all the way to AR n minus 1 plus AR n. Because everything, so these guys here times by r, so we're going to plus the 1 here, plus 1. Okay, great. So what we're going to do here, we're going to subtract the top line. So we're going to subtract the bottom line from the top line. So we're going to do Sn, take away r Sn. So what we can see here is, well, AR take away AR cancels out nicely. So cancels out, AR squared, cancels out. And you're going to notice everything's going to cancel out all the way to the last term. So what we're left with is A take away ARN. A take away ARN. Okay, let's factorize out sum to n. 1 take away r. And let's factor out the a. 1 take away r to the n. So your sum of your first n terms is a 1 minus r to the n all over 1 take away r. And we're done. That's your formula. Proved it. Done. Okay, there we are. So sum of the first n terms, arithmetic and geometric. I'll put a box around it. And we're done. Okay, let's move on. Right, let's look at this. Okay, this is pretty standard. You can just YouTube that. I'm going to just leave that for now. I'm going to show how we find a derivative of sine x, because it came up. This is the 2023 exam, so it's come up. So there's a good chance you might have to prove cos of x in a future exam. So let's have a look at it. So this is the formula we get, and we get given the following information. So let's have a look at it. So f of x is sine of x, and we want to do f of x plus h take away f of x all over h. So you should write every time as your limit of h approaches 0, but for the sake of time, I'm going to leave that for today. But this is what we're looking at. So we want to do sine of x plus h take away sine of x all over h. So double angle formula, we can use it. It says in the question that we can use it without a proof, so that's good. So we're looking at sine x cos h plus cos x sine h take away sine x all over h. So then what we do, we want to factorize out the sine x here. So we've got sine x brackets cos h minus 1 all over h. I am just splitting this up now. Plus cos x sine h over h. And we're told in the question, so this is as the limit of h approaches 0. So we're told in the question, as sine h over h, as h approaches 0, this guy here, sine h over h is 1. And we can see that here. So that becomes 1. And we're told that cos h minus 1 over h is 0, which is here. So what we're left with is sine x times 0 plus cos x times 1. So therefore, as the limit of h approaches 0, the derivative of x equals cos x. And we're done. Proved it there. Nicely done. Okay, you can do the same thing with cos x. You'll get the same. Well, if you do cos x, you'll get negative sine of x. Okay, lovely. Let's move on. Right. Prove for the derivative sine x, sec x, cos x, cot x. So I'm going to do 1. Let's look at tan of x. So this is the formula sheet. We get told the derivative is sec squared x. And we want to use the quotient rule. Okay. I think we get that in the formula booklet. So why do we get it? We do get it. There we are. So quotient rule's there. Okay. So let's have a look at it. Right. So I'm going to rewrite tan of x as sine x over cos of x. Okay. So my quotient rule states that we're going to have u dash times phi take away u phi dash all over phi squared. So I'm going to get that u equals sine x and phi equal cos x. So u dash is cos x, phi dash is negative sine x. Okay. So we're trying to do the derivative of tan x, and we're trying to get sec squared x. That's the goal of this question. Okay. So u dash times 3, I'm just going to follow the formula now. U dash times 3 is, okay, cool. So they multiply by each other. So we're going to get cos squared x. And we're going to take away u times 3 dash here. We're going to take away negative sine squared x. So that becomes positive sine squared x. All over 3 squared, which is cos squared x. That equals 1 over cos squared x. And that equals sec squared x. So done. We proved it. Y equals tan of x, and dy over dx is sec squared x. Nicely done. There we are. Same thing for sec x. You would probably start with 1 over cos for that one, and then cosec would be 1 over sine, and see what happens. Cot would be cos over sine, for example. Yeah, see what happens there. Give it a go. Okay. Right. This is one of my favorite proofs. I'm going to prove this here because this is a question from a mock paper, and I'm going to show you a question when we use it. So, y equals a to the x. So we're going to get the following. Y equals a to the x, natural log of sides, a to the x. So what this means is y equals e to the natural log of a to the x, but I'm going to bring the x to the front, so x times natural log of a, because I'm just using my rule there, so it equals x times natural log a. Okay, so now dy over dx equals, which is the derivative of the power, so the derivative of the power is natural log a times itself. And what we can say here is that this here equals y. So the dy over dx is natural log a multiplied by y, and y is a to the x at the top here. Therefore, dy over dx is natural log a multiplied by a to the x. Fantastic. There's your proof, 3 marks. Right, let's do the following here. So we're going to do the integral. Okay. So we want to integrate 1 to the 2 4x dx. Okay. Well, what this is telling me here is if I integrate this here, natural log a times a to the x, I'm going to get what we started with, a to the x. Fantastic. So for the sake of my question, I'm going to replace a with 4. And I'm going to pull this natural log out. I'm going to pull this out there. So natural log 4 to the x equals 4 to the x. Fantastic. So 4 to the x equals the integral of 4 to the x all over natural log 4. Fantastic. There we are. That's the answer. We want upper limit of 2, lower limit 1. So upper limit 2, 1, 4 to the x over natural log 4. So we're going to get 4 squared, which is 16. So we're going to get 16 over natural log 4. Take away 4 over natural log 4. That gets us 12 over natural log 4. Okay, we want to get this in the form k natural log 2 or some form. Okay, so I'm just going to rewrite this underneath the question. 12 over natural log 4. That equals 12 over natural log 2 squared. So that equals 12 over 2 times natural log 2. 12 over 2 is 6, so we're doing 6. Divided by natural log of 2, I can rewrite that as natural log 2 to the power of negative 1, and we're done. Cool. K is 6, and n, k is 6, and n is -1. Fantastic. Done. There you are. Fantastic. Okay, let's move on. Right, derivative. Prove that x equals sine y, x equals cos y, x equals tan y. Fantastic. Dx. Using dx over dy, take the reciprocal. Great. Really nice question. And sometimes it says find dy over dx and leave it in terms of x. So I'll do both. Okay. I'll do one of these. X equals sine y. Dx over dy is cos of y. Fantastic. So dy over dx is the reciprocal 1 over cos y. So now how do we leave it in terms of x? Well, let's go over here. X squared is sine squared y. Fantastic. And we know that sine squared y plus y equals 1. So if sine squared y is x squared, that means x squared plus cos squared y equals 1. Cos squared y equals 1 minus x squared. So cos y is the square root of minus x squared. And we're done. There we are. There's your cos y. I'll change the colour there. Cos y there. So dy over dx is 1 over the square root of 1 minus x squared. Fantastic. Done. You can do the same logic for the other two. Give them a go. I think for tan y, do I do it sine over x? Maybe not. Maybe you do the derivative of tan y from the formula book. Yes, x squared x, and then you would use equals. I'll do this in my head. Sine over cos. Sine over cos. Yeah. Right. Oh yeah. Equals x squared x. You use that one there. Right. Give it a go. This one I don't know. I'm going to be really honest with you. I've never seen it, so I'm going to skip. Please, maybe YouTube it. I'm already human. Right, let's do one more. Right, lovely. Integration. Integrals of tan x and cot x. Use the test derivative. Fantastic. So this is from the formula booklet. So the integral of tan x is natural log of sec x. Obviously, if I had like tan of 2x, it'd be 1 over 2 sec 2x. But let's do tan of x. Okay. Cool. Right. So the integral of tan over x in terms of dx. Great. I'm going to rewrite that as sine x over cos x dx. So now I'm going to let u equal cos x. Du over dx equals negative sine of x. So du equals negative sine of x times dx. Lovely. Okay, we're very close. I need to make this a negative. So I'm going to make this a negative here, but times it by -1 so they cancel out. Fantastic. So now this here becomes du. Fantastic. So it equals negative of 1 over cos x, which is u, du. Fantastic. Right, we can do this now. So the integral of 1 over u, we're going to get negative natural log of u plus c, I guess. But I think for this case, we can leave that plus c because it's a proof. And we'll keep it in there, plus c. Fantastic. So the answer is minus natural log, and u is cos x plus c. And we're done there. But however, we want to get this sec. So if you remember, that's -1, and we're doing power law. So natural log, and we're doing cos x to the power of -1 plus c. So your final answer is natural log 1 over cos x plus c. And there you are, natural log of sec x plus c. Fantastic. Yeah, we're done. Cot x. Well, cot x is sine x. So let me have a go on it. Right. So cot x. That is going to be cos x over sine x. Fantastic. So let's do the same thing. Let u equal sine x. So du over dx is cos x. So du equals cos x times dx. Fantastic. I've got dx there. Fantastic. So that is here. So we're going to do, so now we're going to become, and sine x is u. So we're going to have 1 over u in terms of du. Fantastic. And it equals natural log u plus c. We've got natural log sine of x. Easy. That was easier than the other one. Plus c. And yeah, we're done. Fantastic. So there you are. 2 proofs there. Cool. Yeah, I'm going to stop the video there. That's hopefully been helpful.